All right. So last time I started to discuss section 7.4, and this section deals with using integration to find the length of arc of the function. So it could be any function y, which is f of x, or x is equal to g of y. So you could pull out x if possible to get a function out. So from interval that starts at a and ends at b, you could use the function, of course, if it has derivative. That's the part that does not really tell, but they don't really tell us, but the keyword is smooth curve. Smooth curves means you find derivative. So it doesn't have any spikes or breaks or any other things. So then we cannot differentiate it at these bad points. But smooth curves means it's differentiable on interval A to B. That's, I guess, the key part here, because otherwise there is no point to talk about that. So anyways, the formulas are here, and I was trying to give you intuition into one, as well as kinda into the other. So right now I'd like to do a problem so we could use the formula. So we could use these formulas, one or the other. So I can try to find the exercise at the end of section where the exercises are. Let's see, do they have interesting trick? Oh, here's 11, here's 12. Let's try 11, for example, that wants us to find the length of arc. See, it's always a good idea to see what they want you to find, right? That's important. Otherwise, how do you know what they want? So you want to read the question, of course. So they want to find the length of arc, and the interval is given to us. How to get a length of arc? Well, we just looked at the little formula that says we need to take a square root of 1 plus derivative of function either x or y. Here we are given function y, so that the derivative of function y of x. So we integrate it with respect to x. And then we need to have the limits of integration here from a to b. So that's our formula. Function y of x. And that's what we have here, so that's great. So now I need to utilize this formula to find the derivative. So let me first of all get derivative. So I'm gonna take care of this radicand first. So I don't want to copy all this integral with a square root. That's just keep on writing same thing again and again, but we want to take the derivative of that function. And this is a composite function, so it's a logarithm, natural logarithm. So its derivative is 1 over whatever the argument of logarithm is, right? And derivative of function sine, which is a cosine. So that's great. We have that derivative, which is nothing else but the cotangent, isn't it? Cosine over sine is a cotangent of x. And this is great. So what do we have for our integrand then? Well, it looks like we're getting something like 1 plus square of cotangent, right? Please notice this is not just the derivative, but it is going to be this type of radicand. And that's great to realize that we can use some special trig formula in order to approach procedure, this antiderivative, and that's what we're going to do. Now I need to take a look at the either formula sheet, or we can try to, maybe why don't I look at the formula sheet? So that's 509 page. So I'll go to the front and see how you could get 1 plus cotangent of x worked out. Right? So you can write 1 plus cosine over sine and utilize this nice, they have it here, Pythagorean identity that will show you that 1 plus square of cotangent is cosecant squared. So once you get this little formula in use, or just work it out, right? Cosine over sine, and then you get same denominator, cosine plus sine. It's 1 over square of sine, and 1 over square of sine is cosecant. But I want to just step away right now into, I think this is very interesting formula if you look at it graphically. And that's why I'd like to maybe go on Google and take a look at something that it turns out not many people saw from trigonometry. The primitives, they say, used to deal with it a lot. So what is this? Well, this is something that I found available on Wikipedia. Did you ever hear about that sign? As I said, it's been known a while ago. Now we're not really using it, but maybe I can try to see if I can magnify it. But the point of story that if you're looking at the right triangle here, cotangent squared plus 1, then cosecant squared is hypotenuse of that right triangle. So it's another way to notice that sum of squares of sides, 1 squared plus cotangent squared, is equal to cosecant squared. That's actually how you can geometrically define cosecant, because we know cosine is, right, the quotient of opposite to, right? So what is that? Cosecant, 1 over cosine, and cosine is opposite to hypotenuse, and from the fact that the adjacent to hypotenuse is 1 over hypotenuse, it's cosecant. So it's worth to think about it. Now notice that there were other functions such as versine or coversine, kind of similar here, that people used to work with, but not any longer, right? So there's some other functions here, and they all coming out from the tangents to the unit circle. So I think it's interesting. That's worth to think about. But anyways, I don't want to carry it way too far, but it looks like that's what I didn't see any trig textbooks that being printed nowadays that introduce this functions, but in Wikipedia. So that's interesting. Right? So anyways, where were we? And of course, this is all being utilized, and sometimes people might ask how those primitives back in 1600s, like 15th and 16th century, would cross the oceans, and how would they find where they were actually heading to? Well, they probably knew something that without navigation that we have nowadays, we might utilize this interesting other approaches. So anyways, we are back to page 509. So I say, Alex, so what's the point of your story? Well, the point of story is that we have, I need to, of course, get my pen, and that we have this square root that turns into cosecant squared. And that's great because we have square root extracted from cosecant squared, so all you need to do is just integrate cosecant. Cosecant. So what's the antiderivative of cosecant? Cosecant cotangent? I say, really? Did you memorize it? Yeah. So it's ln of cosecant x plus cotangent x. So again, if you look at the little table in the beginning of the textbook, the one that I was discussing in the beginning of our semester, I don't want to do it again, but the point of story that's for cosecant, if you integrate it, you multiply by cosecant plus cotangent, divide by cosecant plus cotangent, then turns out derivative of denominator will become your numerator, and that's how you get 1 over denominator, 1 over x, and antiderivative is ln. So it is really something that is present, and also it's with a negative sign, because when cosecant is negative, when you get secant, it'd be positive. And now I can put my limits of integration that they wisely provided me with, and they are those limits somewhere here. Pi over 4. So pi over 4 to 3 pi over 4. Okay, that's great. So now we're gonna put them in 4 over 3 pi over 4. And at this stage, you could just use a calculator and put this in if you want to get the answer quickly, or if you like to get the ideas of 3 pi over 4 angle and pi over 4 angles, how we working with those. So cosecant is 1 over sine, right? So if you think of pi over 4 angle along the unit circle, the cosecant, let me write it out now. Now it's going to be tedious. Now I have to write that. Upper is pi over 4, right? Plus cotangent. And then also pi over 4. And then I have to subtract negative. So this is going to be to add another ln. Oh, now it's 3 pi over 4. Cosecant 3 pi over 4 plus cotangent. Okay. So we'll now need to refresh a little bit of knowledge of trigonometry, right? So let's do that. We're gonna see that cosecant 1 over sine. So sine of pi over 4 is, use red, square root 2 over 2. Sine is 2. So 1 over sine, and if you flip it, it'd be 2 over square root of 2, right? Because cosecant is reciprocal. So what about cotangent? Well, for cotangent, I use tangent because it's 1 over tangent. So with pi over 4, tangent is 1, right? What I'm doing is attaching line of tangents and also using the other definition. So line of tangent, and again, it's 45 degrees, and we got value is 1. Again, you can put in calculator. So reciprocal of 1 is 1. Okay, so what about 3 pi over 4? Well, looks like these things can only change your sign and for cotangent. So for taking the 3 pi over 4, which is going to be the one here, right? It's good to know this is a fast way to use so-called line of tangents to get values of tangents or cotangents, which is 1 over tangent. So it looks like 1 pi over 4, 2 pi over 4, 3 pi over 4, but we can also go down to the line of tangents and see that -1, which is reciprocated, and it is still -1 if I take its reciprocal when I take the cotangent. And what about the cosecant of this? 1 over sine. Well, sine of 3 pi over 4 is still its y coordinate, and it's the same. So the same means it is square root 2 over 2, but reciprocated, which is 2 over square root of 2. So notice that we have one ln taken of sum of these guys and the other of difference. So maybe I can just write it down. I know it takes a little time, but one is with a negative. So let me put minus, it's okay. So I'm not gonna commute them, we'll just keep them. Sine, now it's square root 2 plus 1. And then we add it with square root 2 plus 1 is positive, so I don't need any absolute values anymore, but whatever, right? Because if you take absolute value of positive, it is still the same thing. It's a square root 2 minus 1. And say, Alex, how come it is square root 2, not square root 2 or 2? Well, remember, we took a reciprocal, and now we can also factor your numerator. That square root 2 is radical 2 times not radical 2. Same as radical 2 squared or just a 2, but this enables us to cancel. So we end up only with root of 2, right? Minus plus 1. So that's why it's standard. Again, by saying it's standard because I saw it in lots of exercises, so one needs to realize it. Now, using properties of logarithms, it's ln a over minus ln b, so it'd be ln of root of 2 minus 1 divided by ln of root of 2 plus 1. So this is going to be exact answer. Sometimes, remember, in the college algebra classes, they ask, get exact answer. So I gave them exact answer because otherwise, if you put in a calculator, it'll be something point, dot, 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 whatever decimals, and then you round it. So it's approximated answer. So this is exact answer. According to the formula, if you subtract logarithms, then it'd be logarithm of a quotient. So we're utilizing lots of little properties of logarithms here. Well, that's why I decided to select this particular exercise because I think it is a little bit different. It uses lots of refresher from previous classes. So I think it's worth for you to maybe over long weekend. Oh, actually, it's not a long weekend for our class, right? Over a long weekend to get the little bit of, I guess, writing. That'd be nice. So anyways, I want to add one more thing that this section is discussing. And since it's a long weekend that we're not going to get to experience in this class because we have meeting today, and then there's a long weekend starts. It's Lincoln's birthday, and on Monday it's Washington's birthday. Actually, college is still open tomorrow, but everybody has long weekend, but not us because our class resumes on Tuesday, but everybody's enjoying it on Monday. So I'll just finish up with this section and let you enjoy the long weekend. I guess that's the best I can do. So I'll do one more exercise. I just want to add, talk about nice picture that I just saw here. It's a beautiful picture here and the story attached to it. So it turns out that now you can produce three-dimensional figure. And again, by doing the revolution. So you can revolve your given arc, like we have here, around some axis. And then notice there'll be empty spot inside. So it's no longer be making any sense to talk about the volumes because volume of two-dimensional surface is not making sense. It's going to be zero because inside is just hollow because it's just a surface. We can find just area of the surface. And that's the point. We cannot produce volume because it's empty on the inside, right? Because what they did is they took some kind of line in this case and they rotated it and they produced this like an empty surface. And well, they can find the area, not volume, but area. So that's something to watch out for. So that'd be in terms of squared units. And the area analogous 2 pi r, 2 pi times r, that's the area of the circle. And then you need to multiply it by length of that arc length. And the arc does not have to be nice and straight as a segment. It could be curvy and we could still use the same thing. So they have nice pictures here down below. So there could be some nice, like a vase, hollow on the inside, so you can find the surface area of that vase. Doing the exact same thing. So they take 2 pi r, so instead of r, they use values of function, since it varies, since radius is not constant in this case, radius is here, r, and in the other point, there would be another radius, so it varies. In fact, you could find some tricky surface also rotated, the tricky curve also rotated and produce surface. So that's the power of integration. So you could, I guess, no care, don't care about this. It's kind of hard to get, but I hope that's the surface of revolution. So the point is that the curve could be just about anything as long as it is smooth as we can find its derivative on that particular interval from A to B. So the same exact analogous story to what we already saw before. So we need to multiply that radius, but by the surface length, because the surface length is not the length of segment that connects our points A and B, because it's really could be quite not like a segment. But if you cut it in lots of segments and then send n to infinity, you get very good approximation. In fact, when you take a limit, you get exactly the integral. So this part they call this dl. And that's our derivative of right? That's here. Derivative of our function squared inside the square. So we extend it to one more step to use with three-dimensional space to find the surfaces. Well, I'll do one exercise. I can actually trace one here. That'd be probably better thing to do. Example 6, for example, here. And for that, I need to stop sharing to maybe I'm not gonna stop sharing because I wanna still use the formula here, so just clean a little bit of room. Okay. So let's see how how we can utilize it again when we move to the third dimensional situations. Let me clear. So it looks like now you're rotating cubic parabola, right? In this example 6, you're trying to rotate the cubic parabola, and the way you're rotating it is about the x-axis. They nicely show in the picture. So this little part, when you rotate, you produce that particular part, like a cone or something. And then we have a point here, and we see the radius of rotation is going to be same as function f of x. So the radius is here. They call this little r. And then 1 plus y prime. So since function is here, then I need to know what y prime is. And derivative of x cubed is 3x squared. So now you have 1 plus 3x squared, and this is squared. And that's extracted square root. So please notice that when you try to integrate, and you integrated it from 0 to 1, see, for themselves, they like to have nice limits, 0 to 1, that's great. And 2 pi r, so instead of r, we use our function x cubed here, and 1 plus the derivative squared inside the square root, which is going to be 1 plus x to the 9x to the fourth, and the power is 1/2. So why would they put 1/2? Well, because they want to use a substitution. They want to replace your radicand, and standard way to substitute is to just right away replace the whole thing with new variable, right? And then you take derivative, so it'll be 36, 4 times 9, right? 36, and x cubed, power is 1 less, with dx, which is du. So we took derivative, which is great. And now we look at what we have for the integrand, and we have just x cubed and we have dx. So we don't have 36, and that's fine. With numbers, we can just put them in denominator, right? So that way you nicely replaced everything you have. Numerator will be u du, and du is still over 36. 36. And there is a radicand also here, and that radicand is actually here, is what you have as a u. So it'd be square root of u, or u to the power of 1/2. And that's how they produced powers 1/2, or powers of 1, which I could write as 2/2, right? 2/2 is 1, is just a u, and 1/2, and that's where they get in the power of 3/2. See, they trying to integrate the x cubed. So that is, see, it's worse to write it. So that's u and then du, and that's a square root from that u stuff. So we are doing what? Now we have the antiderivative to take off. So that 36 comes out. And then we also have 2 pi that I need to copy, right? Right? So I do substitution. And it's u to the power of 3/2. So now to take a antiderivative, I need to add 1, right? So to add 1, not sure what they have here. I don't want to get really deeply into it, because when I took this whole thing happened to be my du over 36. So there is no u here. So we integrate 1/2. Okay. Once I did substitution, then everything becomes clear, because otherwise I think this step is what they expect you to do, and that's what I'm doing. So power of 1/2, so that will be 3 over 2. Because you add 1 when you take antiderivative, right? And you need the same 3 over 2. And then you also can reduce by 2 your front factor, such as a number pi over 18. And then you will be able to put limits of integration a little later, 0 and 1, after you finish up with the substitution. So what else do I do here? Well, looks like I can cancel a little bit more. So it becomes 9. And 9 times 3 is 27. So it will be pi over 27. And then we have u to the power of 3/2. So since it's halves, it will be square root. And this stuff inside the square root will be cubed. Right? And what's cubed instead of u, I put back my original integrand, radicand. Sorry, radicand. 1 plus whatever it is, 9x to the 4th. And then you finish up with this limits 0 and 1, and they are just beautiful. So you can just put 1 on the upper one, right? So it'll be 10 here, right? So 1 here, so it'll be 10 square root 10. That's what they have, which is going to be also cubed, and then minus. What do you get when I produce 0? From 1 to 0, so 0 will kill that x piece, and it'll be just 1. So that's why they have just 1. So they got the result. So 9 times 3 is 27 in denominator, and that's 10 to the power minus 1. So it looks like you really want to work out these things, and that's the point why I ask you to also copy down basically ready solutions, which I think are a little bit better than we have here, because here lots of steps missing, and they expect you to write it down yourself, so you fill the gaps. And that's the point of pretty much any math class. You want to make sure you do correct solution, but you also make sure you want to do the algebra correctly, so they don't do much algebra here. They skip it, leave it up to you. So fill the gaps. And that, I think, will be enough for today. As I said, in the spirit of coming holiday, I will let you go today. No quiz. Last time, by the way, was a quiz. Everybody did it absolutely correctly. So that was integration with respect to x, I remember. So everybody did it right who submitted quiz. If you did not submit it yet, please do that. And I guess that's about it. I think happy President's Day holiday. Enjoy, and we will continue next week on Tuesday. Thank you for coming over. Thank you for paying attention. I'm going to stop recording, see if you have any questions right now. And if not, have a great day. Feel free to